Okay, welcome everyone to today's Explore and Learn session, where we continue exploring and learning about various factors of the Rulliad and various other computational foundations of science. So Carlos is going to lead us today in discussing rewriting specifically, which seems like a simple kind of thing once you understand it, but it might be more mysterious than we initially could think of. And Nick is joining us, and myself. We are going to see what Carlos has to show us. So please take us away.
Yes, thanks, James. So today we're going to be introducing the basics of rewriting. So this is for any one of you who has maybe heard the term, and we obviously throw it around in here at the Institute, and want to get some basics and some sort of preliminary notions of what to think about and how to maybe imagine the how this became relevant for the Institute and so on. So I will begin with a very brief explanation. So if I can share this one here, I think everyone sees it, right? So it's actually very elementary, and in a way, it's almost like going back to kindergarten. And you might be asked, there's a simple counting task. If I can click on this, this may be a simple counting task, and you're told, there's like this few blobs, and we want to count them, and you're like, okay, that's a very difficult task. So let's break it down. So we can see that there's a thing here, easy enough. There's another group of things there, easy enough, and then there's a bunch of stuff there, which I still don't understand. And then certainly there's two things over there, and then there's this kind of whole thing together. And maybe next year of primary school or something, that you're taught some arithmetic, and you can actually say, well, I can count to 1, I can count to 2, I can count to 3. And you have some basic idea of what addition and multiplication mean, and so you might write this expression. Say, I have a formula, I have a theory. I think the number of blobs on the screen equals this expression, because I know what 1 is, I know what 2 is, I know what 3 is. I know that putting things together amounts to plus operation, and when I have rows of things, I can basically use times, because I can see 2 groupings of 3 things or 3 groupings of 2 things, so I can write 2 times 3, right? So you say, okay, right, but that's still far from knowing the number of, because obviously counting to the whatever number this many balls is or many blobs is way too difficult for us in primary school. So we have to go step by step and little by little. So then you're told, actually, you can operate this addition and multiplication operations that you wrote down. So I say, okay, right. So let's see little by little how that works. So I can look at the expression. I see that I have 1 plus 2 and I have a 2 times 3. You're a very clever pupil back in kindergarten, and you know that 1 plus 2 is 3. So you say, okay, the first time I see that, I'm going to rewrite it, and I'm going to write 3, and I'm going to leave the rest unchanged. But on the other hand, some other clever pupil might come around and even more advanced, and you say, hey, but 2 times 3 equals 6. So 6 is for this symbol, so you write it on this side this way. Like, okay. And then you say, well, but if I apply my knowledge to your expression and you apply your knowledge to my expression, we both get to the same expression, which is 3 plus 6. And then some really advanced student comes around and tells you, actually, 3 plus 6 is 9. And then you're done, right? So, I mean, obviously, this is a bit of a joke to say that this is very sort of joking way, but this is the foundation of how we do mathematics and how we learn to practice mathematics, right? So obviously, when we get to the stages where we're formalizing our theories and we are setting up frameworks that are either maybe computerized in really intricate databases and all manner of systems running, or in complicated corpus of theories, at the foundation, when a human is operating in mathematics, most of the time, this is what is going on in their heads. And I wanted to give this example. Is sort of like similar to what children go through when they learn like the priority of operations and things like that, because in some sense that's essentially what algebra is all about. And some people might want to extend and say this is what mathematics is all about, right? So the key idea here was the notion of rewriting. So I want to give you another example from a field of mathematics that is very modern and certainly doesn't sound like preschool mathematics or primary school sort of like debates among pupils, and that's category theory. So in category theory, you have this abstraction of many different notions in mathematics or science in general. So here, X, Y, Z might be some sorts of systems or states of a system or objects in some abstract sense, and F and G might be processes or programs or functions or processes between them, right? And so you have this notion that when you have a process and then a process, if the domains of these processes, so the actual stuff that the processes involve, they can be composed. And so diagrammatically, we express this simply by saying you have an arrow from X to Y, you have an arrow from Y to Z, and you do this composition that is similar to what we call also a transitive closure, basically just closing the diagram for it to be transitive. So of course, this has implications, and one can use the rewriting approach to detect things such as Confluence. And this is just a brief example before we get into sort of a bit more of the explanation of what rewriting does for us, which is, in a very similar way to the sort of basic arithmetic example, you can think of this diagram that suddenly has two patterns that resemble the rule that we can apply. So the rule that we can apply is something arrow something, and something arrow something goes into an arrow between the two ends of the diagram. So when we look at this diagram, we indeed see two matches of that pattern. So on the first hand, we have ABC. Second hand, we have BCD, and these are both rewritten independently. So first one we get something like this, and on the second one we get something like that. And of course, similarly to the case of arithmetic, we now can apply the same pattern again to these two diagrams, because indeed there is an ACD pattern and there is an ABD pattern, and both can again be rewritten by the same rule, and therefore give rise to two arrows from A to D, and we represent them in the same diagram just because they look like the same kind of arrow in this sense. And of course, they have different names. If we're using this notation for composition of arrows with brackets and maybe the circle dot or something, these have two different names, and the fact that they are associative really mean that there's only one such thing. But this is a bit beyond the point. This is just to illustrate that rewriting is at the core of preschool mathematics all the way up to what most people consider modern mathematics and really fashionable and cool stuff like category theory, right? So in a sense, this is rewriting, right? In a sense, if you followed my explanations for the last 5 minutes, you understand what rewriting is all about. And in a sense, you have been doing rewriting all your life. I mean, in a sense, the word rewriting evokes something quite familiar. It's not like saying factor or something that is more esoteric sounding. Indeed, rewriting refers to a mechanism that assumes the existence of some sort of term, some sort of entities that have a certain stable nature that can be sort of comprehended as units. And there's some sense of procedure by which you deform or alter or transform those entities into entities of a similar nature. And then you say that you are rewriting them because you always think that these processes are reversible in some general sense, that information can be created or destroyed just at the whim of what the actual process is dictating. So there's very little assumed in the way of what the processes are like, but there's a lot assumed in terms of the fact that there's a process, right, and the fact that there is a input, output, and so on. So anyway, I think I will move to the whiteboard now.
So just a quick question on that: the difference between rewriting and, let's just say, like an equal sign, because sometimes you could say that this thing would just be equals to that thing, is that there's an input and an output, like explicitly it's like a directed equality or something like that?
Oh, that's a very good question, actually. So yes, typically if we're really going back to primary school, most people don't write arrows. I guess some people, when they are learning, they just scatter expressions when they're trying things out. But most of the time, the teacher will tell you, no, you have to say this equals this equals this equals this, and equals the solution to the problem or something, right? Or maybe you are solving an equation, so you're grouping variables and you're doing all this elimination or whatever. So in rewriting, you don't assume anything other than the process. So equality of terms is something that is either pre-assumed to be exact identity, so the fact that two objects, two terms are indistinguishable, so something that allows you to tell that they are two different terms. That's what inequality is, and the complement of inequality is equality. Or you need to define some constructive way to define equality, right? So you would have to say something like these two terms, if they are confluent, meaning that there exists a future in which they are arriving at a terminal state that is in both futures, then you can say that this is an equality between them, right? And so this is typical of algebraic rewrite systems, right? Like the one that I showed. So if I go back to that particular example, actually, in here, you would see that, right now I have two. I mean, obviously I begin with a single expression, so it's not surprised that it should result in a single number, because that's just computing a number. But imagine that I don't give you the first expression, I just give you those two different expressions, right? They just look different. I mean, you're not a very clever kid. You don't know, you can't count up to 9. So it's a bit too difficult to say, are these equal? Are they actually equal? So, if I am literally like blocking off half of the screen, so I only see 3 plus 2 times 3 and 1 plus 2 plus 6. If I only see those two things, one formal way, actually, in some formal systems actually do this, to say that these are equal is, if you apply the rules of arithmetic and you end up in a common terminal element from both, then, so indeed this case, right, then you can assert that these two are equal. And in this case, it is literal equality, right? Like that's exactly what you would write in the school homework, right? Like you would say that equals that, because the value when you compute it equals. But it's, equality is a funny thing, because when you think about it, it's easy to say equals, 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 but you're writing two things that are literally different, right? These are two different expressions that you're writing down. So saying that they are equal involves, I mean, we are so used to this because we are presented with this notation from when we are 5 or something. We're so used to this that it's almost second nature to just use equals, 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 and it's like part of life. But when you think about it, it is a non-trivial thing, right? So I really like your question here, because it's perfect to discuss this beforehand, like before getting to some of the concepts in rewriting systems and so on.
Could you say that there are certain types of rules that when you apply, there's a presumption of equivalence? So, for example, addition, like you can apply the addition rewriting to that 1 plus 2 into a 3. And when you do that specific rule application, it's proven to be equal, something like that. But what you're doing is you're computing something, and then it's just like those rules will give you equivalence or something like that.
Right. So
or does all rewriting always result in saying something could be equal to what it got rewritten to?
So here's the thing, right? In rewrite systems, terms, as I said, terms carry this preconceived notion of identity. And I say identity instead of equality because, not to get, conflated with the language. So the sense of identity means that each term, it is sort of self-evident whether it is equal to itself or not, right? In other words, you have a well-defined set of terms, right? You know that 3 looks different than 4, like the number 3, the character maybe, the numeral character, or 3 and 4 look different, so okay, they are different. You just have a preconceived notion or a pre-established notion of identity, meaning that they are separate. However, if you have this sort of situation where you have 3 plus 2 times 3 and 1 plus 2 plus 6, these are very different looking terms, right? They just have brackets in different positions, involving different symbols and all this stuff. So to state that these two are equal must come from some external information to themselves, because just by themselves, obviously, they as terms, so a term, this is an important, that's why I'm really enjoying that you mentioned this, and we have this little conversation before going into the rare systems proper, because it actually clarifies a lot. Terms themselves don't have any semantics in them, at least in the perspective when we are doing just pure rewriting systems, right? Like the terms themselves just have a way to exist as an internal structure, but they don't immediately have a meaning, right? That they don't tell you anything other than, hey, I'm a term, I can be rewritten according to whatever rules you want to define. And, if you give me some rules and you give me some, successors or sort of some generations before I might exist in their future, or if you propose some potential other terms, they might be in my future under some rule. I mean, that's basically all they can do. So if you see those kinds of symbols, it's almost like when I said, this is, we have to go back to kindergarten, is because I really want us to be back at that mentality when, you see this kind of symbols and you're sort of mystified. It's like, what the hell is this, cross and two and times? Like, where are these things? So that's kind of what rewrite systems see. Like they just don't, they're kind of dumb. Right? They don't see all the algebra that you're going to be implying. And but the reason I'm really emphasizing this point and sort of taking the time in here is that, in my opinion, one of the powerful aspects of rewrite systems is that their causal structure is precisely what allows to articulate these kinds of things. And equality is the perfect example of that. That's why I welcome the question so much, because everyone from primary school is used to writing an equals in here, right? So let me see if I can very quickly do it here real time. So everyone is very, very familiar with just writing an equal sign between those two things, right? But obviously, that necessarily must be a non-trivial statement somewhere. In some framework, there needs to be some kind of procedure that formalizes what that equals means, because it will be obvious to state something like 3 equals 3. Sure, there's no fundamental, I don't know, profound statement in saying that, but there must be something more profound than 3 equals 3 in 3 plus 2 times 3 equals 1 plus 2 plus 6, right? So the what I'm saying here is that the formalization of that equality is actually done via the causal properties or the causal structure of this rewrite system. And it sounds very fancy to say the causal structure of the rewrite system. All that means in this particular context is that, take these two states, you ask, is there a terminating state, a terminating term that is in the future of both, right? And if the answer is yes, then you're sort of welcome to say they are equal, because if you're interpreting this as sort of calculation devices, each of these terms represents some little calculation device, and you conclude via this knowledge that there is a future term that is terminating, a future state that is terminating, then you know that the calculation will terminate in a single value, and therefore you know that the value they compute are the same. So that's
Confluence, basically, right?
That's Confluence. That's what we technically call Confluence. So in this particular setting, that's how you define this. But of course, you can define relations that are more subtle than that. You might want to say things like, given a term, I'm gonna relate all the terms that are in their previous 2 generations, right? And then you suddenly relate a bunch of terms, but they wouldn't be equal in the sense that we would normally think of equality in, say, in arithmetic. But then nonetheless, these relations are well defined, right? Because you just look at some causal structure of your rewrite system and basically ask, can you derive this expression from this other one? And if the answer is yes, then you say they are related. And when you're thinking of algebra, most relations you're going to think of as identity or equality in an algebraic sense or in a set theoretic sense. But when you're thinking about many other things, like, I don't know, if these things were programs, right, then, and they are being rewritten, then you might be thinking in terms of, are the set of outputs the same or not? And this is a question maybe of quantity. Like, if you have a finite set of outputs, how many outputs are the same? How are you diverging from one program to the other, and things like that? How efficient are you? These kinds of things. You might ask a lot of questions about the terms themselves once the rewriting of them has, it's implemented, and you can just guess and count, not guess, sorry, but actually count or probe the system to know what it's doing. But that was an excellent question to sort of preempt the discussion around rewriting systems. Good to move on?
Cool, yeah.
All right, so I will now open the whiteboard. And I will turn off my camera so that I can write with some ease. All right. So, rewriting. Oops. there are two ways in which we want to think about rewriting. The first aspect of rewriting is what I'm going to call the causal structure. And I will say in brackets here, directed graphs. And the other is about term syntax and semantics. Which, because we are the Wolfram Institute, we typically will think about hypergraphs or strings. And so on. So when it comes to rewriting, there's really two very different aspects of what one can be thinking about. And these are essentially classified in these two categories. And the reason I separate them is because the kinds of tools and the code even that we are developing for each of them is sort of separate, and they are in a way independent. Apologies for the loud noise. So in terms of the causal structure, there's the way, when you think of a rewrite system, think of the example I just gave, the arithmetic one. You have the numbers on the one hand, the symbols and the plus sign and brackets and whatnot, and you have the structure of how the system evolves, right? So the causal structure is abstracting what the terms sort of involve. And so you have, the example I gave, we had something like that. We had the expression, 1 plus 2 plus 2 times 3, and then you do the 1 plus 2 on one side, and you do the 2 times 3 on the other side. You have, so you pay attention at the terms, and there was another term that was 3 plus 6, and then was a final term that was 9, right? So that's the first thing you identify. You identify this sort of broad structure, and then you note how you flow on with those terms. In this case, it was just arithmetical expressions and usual rules of arithmetic. So the way we flowed was, we first did the 1 plus 2, or we did the 2 times 3, or we did the 1 plus 2 again, or we did the 2 times 3 again, and then we got the same expression, and then we got the 3 plus 6, and we just did a single addition operation, and we got the 9, right? So I'll fill up with the example now so everyone is clear. So here we did 1 plus 2, that was 3 plus 2 times 3. Here we did the 2 times 3, which was 6. So here we get 3 plus 6, and finally we get 9. Okay, so the causal structure, by the causal structure we mean the things that are not terms, right? So the causal structure here, I'll highlight if I can, is this stuff. Right? So the fact that we have this directed graph, that's the causal structure of the rewrite system. So in a sense, the causal structure of this rewrite system doesn't know anything about the terms. Right? It's just about where's the topology of those terms under the rules that we are establishing. Right? So what this is basically telling you is that if you want to get an expression that looks like 3 plus 6, you can't apply just one rule to the expression 1 plus 2 plus 2 times 3. You have to apply at least 2 rules to get there, right? And so if, similarly, if you want to get to an expression to 9, you can apply a single operation to get from 3 plus 6. So you can imagine, that, of course, that if you increase the number of terms in your scope, then these things become huge, because obviously there's a lot of partitions of integers, and there's a lot of factors of integers and so on, and so expressions can get quite complicated. But typically, a rewrite system will consist of a given initial state and a set of rules. So okay, so I'll get into the formal definition in a second, because the whole point of today is to give that definition, and so that when we talk about a rewrite system, everyone has a loaded up definition in their mind. Now, the other thing about rewrite systems, of course, is the sort of term syntax and semantics. So the semantics I don't really care about too much today, because semantics could be very broad, and we could be thinking about many things. Of course, as you saw, the kind of rewriting diagram that you got for arithmetic was very formally similar to the one that you got for composition of morphisms, but the semantics that are implied are very different. Right? On the one hand, you're thinking about just adding stuff together in different orders, and the other is whatever, composing production protocols in a factory somewhere. I mean, they're quite different, but when understood as the rewrite systems, they become almost indistinguishable. Now, the syntax is important because this is what rule application is going to be predicated on, right? So basically, if I have something that looks like this, right? Oops. Yeah. So you have an expression that looks like that, right? Which did occur in our example rewrite system. So there's a sense in which I can take this, I know these symbols, and this can be operated to give 3, right? So this is something that you have to either define for your system or have some sort of systematic procedure to generate it. So in this case, because we are using a symbolic system, the procedure involves some kind of complicated symbolic procedure, some symbolic framework, because this is a human numeral system. So it's going to involve a lot of tradition and whatnot. But we could be much more simplistic in sort of the vein of cellular automata or discrete dynamical systems and things like that. And you could have something like, just draw this kind of thing, right? And whenever you see 2, you write another 1, right? Which this you might think is +1 or something. You could interpret it whatever you want, but basically, whenever you see a term, there's just 2 dots, just add a new dot, right? And write 3 dots. So the semantics here are very debatable, right? Like this could be, +1 function, but could also mean, this is some kind of like cell reproduction or, genetic descendants. Like it could be many things. The point is that the syntax here is just dots. So like 2 dots go 3 dots, that's it. There's no more complication, right? So, but of course it matters to the whole business of rule application, what the structures are. Because okay, if that's my rule, if I have an expression that looks like this, how does it apply, right? Does it take all the subsets? Does it take only one? These are the kinds of things that matter to when understanding how a rule applies, right? So typically, you're going to scan for all possible applications of a rule. So if you have an expression that, in this case, is just a bunch of dots, right, and we're just counting dots basically, then indeed you're going to have as many different applications of the rule as there are pairs of dots. But it so happens that in this particular syntax, when I apply the rule here, so if I take this as my starting state, right, and I take this pair of dots, this will give me a future that has the same dots, and then another one, right? Because of those 2. If I take these 2 pairs of dots here, I get the same thing. If I take those 2, and so on, right? If I take all the pairs of 2 dots, I will get many different terms. But it so happens that in this particular syntax, all these terms are identical, not equal, because we want to reserve that notation in case we want to be more precise, but they are identical, right? They are the same symbol. They are the same syntax. Therefore, there's really no multi-way bifurcation here or multifurcation here, but we actually have a single future for this, right? Sorry. So I had 5 here. And therefore, there's just add 1, right? So now I have 6. It doesn't matter the distribution, because this is just counting dots. So this is just to emphasize that it really matters what it means to find an expression. right? What it means to actually have found an expression and what it means to output different expressions and to be technically different or technically identical or technically, that's what I mean by term syntax and semantics. So these are two quite separate aspects of rewrite systems. In a way, most people traditionally, when they speak of a rewriting system, they tend to mean the left-hand side here. They tend to mean the causal structure of a rewrite system and not so much the term rewriting involved in producing such causal structure. Nonetheless, it is extremely important for us in sort of binary and discrete applications of rewriting approach to actually do the term rewriting to the full extent and to pay attention to exactly how term rewriting works. And in a sense, that's what we've been sort of grappling with for the last year or so in trying to formalize and trying to implement hypergraph rewriting in particular for many of the applications that we've been doing. So anyway, I wanted to really highlight that there's these two components, and then for the rest of today, we can just talk a little bit about each of these sides and maybe get into some more details and some buzzwords. Let's just give a sense of the buzzword and what they mean, and just end with that. But any general questions at this point?
Yeah, for sure. So I might have missed it, but I've got a fairly I think I formed an idea of syntax. So it's kind of like the words, like how you're defining the words. So it's either like kind of like the symbols. Did you differentiate syntax versus semantics? What is semantics of the thing?
Yeah. So actually, you said words, and that's the other example that I was going, because that's the most classical example of rewriting. But before I say that, so I'm separating syntax from semantics because syntax is the literal symbols that you're getting, right? Like these are the literal graphical entities or data structures that you're using to encapsulate your states, what you call states or terms, right? And semantics is I mean, in a sense, I had all these discussions with computer scientists where I was trying to really push them to the edge and say, isn't really all syntax, right? Is there there's no real semantics in a sense, right? It's just a matter of where you place your lamppost. It's like if you base yourself in some syntax and you point to another syntax, then you say that's the semantics of your syntax, but that's just a matter of sort of like perspective in a way. But really, semantics typically refers to another system that already has a behavior that is known to you somehow, right? That's what you would mean, like that's why you would say something like meaning. And in the case of arithmetic, it's very clear, right? Like arithmetic, like all those symbols, one and the cross, just straight, the cross, turn 45 degrees and so on. Like those are just like dashes on a piece of paper, right? But the meaning of those dashes is meant to be like counting stuff, the almost like the physics of counting, like when you get objects around and you start counting and you group them together, and that's why I have the example of like the blocks. And, that's the semantics of the system, right? If you want, this is the syntax, right? What it's written here is the syntax. The semantics could be the process of counting that system that I showed, right? So that is I don't know if Nick, did you have a better way to explain this?
Oh, I don't know. It depends on the context, I guess. Usually, when you talk about syntax, it's maybe some kind of language is inferred, right? So, as you said, it's just like a bunch of symbols. But maybe there's more formally, you have to define a language and what is this, in which these symbols are actually expressed in. But semantics is just the way how those symbols are transformed into some sort of maybe instructions. Maybe that has to be run on some computational engine, like a Turing machine at least, right? So maybe that's the minimal way to define semantics over the symbols. So you just have a language, which is just like those hollow symbols that doesn't mean anything, but then you have to have a way to turn them into some form of instructions. Maybe just in a form of thoughts that you're just thinking about them. So that's already semantics.
Yes. Yeah. And I always had this pushback when saying, because many times people talk about semantics almost as kind of a a target, you begin with a formal system that is sort of devoid of life in some sense. It's just like lifeless symbols and hollow symbols. And they say, but then the semantics are this, and they give you a system of symbols that is nonetheless either more familiar or has been around for a long time, or people have an understanding of how that fits in the world somehow. And then they call that the semantics of this other system. And so, I've sometimes pushed back to some of these computer scientists because I said, well, really, both are made of the same stuff, right? Like, it's just that in some sense you're placing the burden of one being the reference for the other, right? So there are some contexts in which this distinction is meaningful. In others, as Nick says, you can, in a sense, really distinguish the pure symbolic infrastructure, which sometimes could also involve the sort of the what is allowed, right, in your terms. Like, some people think of that as syntax, right? It's like, these are possible terms, so that's just part of the syntax. But the way you manipulate the terms, or the terms relate to each other, and so on, that's when people start to talk about the semantics of the term. But
you could almost say semantics might be the rules, but it's kind of like a philosophical point, syntax and semantics. You can get quite deep with it, I suppose. But depending on the context, there's kind of well-established ways in which you can talk about those things.
Certainly, I think you could say that the semantics are the rules, although it's very hard to just say that they are just rules.
Yeah.
Because then it doesn't really, like, to me, that doesn't confer the meaning, because in a sense it's almost like that's the machinery doing a thing, but only when you want the machinery to do the thing, not it's
like which rules you choose to have as options on the semantics, maybe something like that.
And for me, what's crucial about semantics, and Nick, I would like to hear your opinion, but for me, what's crucial for semantics is some kind of mapping to a different thing. It's like to a different system that has some other form of foundation. And ultimately, in my opinion, this should always end up in some kind of natural system, some kind of empirically correlated system that you can say, hey, this is what I mean by that, right? This is what I'm pointing at in the world.
And that's what mathematicians are always trying to do in some way. They're always trying to find, like, maybe a correspondence to talk about the properties of one thing as opposed to this thing that's been studied, and you study something new. You try to find how these things are connected in some ways.
Maybe there's an analogy would be like this, like semantics is like one true thing, is like an object in a physical world, right? And all the possible syntactic ways of expressing the same meaning is just like a different reference frames or a different choice of bases. So in a way, it's like, yeah, we call it semantics, but in order to actually talk about what the actual meaning of this only existing thing is, you have to express that in some form of language. And that's why you have to pick a frame, right?
Yes.
A reference frame, how to express this semantical meaning in some form of syntax. So in a way, maybe that's the analogy also.
Yes, I've heard this analogy before, actually, and I like it to a degree, because and in fact I think I was using it myself, to be honest, when arguing that the distinction between syntax and semantics sometimes becomes a little bit tenuous, because you have several you have in the geometric analogy you just mentioned, right? That you have intrinsic entities like points in space or shapes in space, and then you have coordinate expressions of those objects, right? Of course, there are infinitely many coordinate expressions to the same point, but even in my sentence there, I said the same point. There's only one point, right? So you might be thinking, okay, that's the meaning of the multiple syntactic expressions that can represent that. But I think my pushback, I mean, it's not a pushback to your definition, Nick, or anyone's definition, but my sort of comment here is actually the way you formalize that many coordinate expressions refer to a single point is again in another, symbolic system that is, mathematically rigorous and whatnot, and computable in a sense. So it feels to me more like this is just some kind of correlation or mapping between.
Well, yeah, the transformation. You have like a transformation function between your reference frames. You have a reference frame, and you obviously have to have a way to transform between them, right?
it's kind of like
Yeah,
it depends on the observer at the end of the day. The observer has to take a place somewhere. It has to start somewhere, and then that's kind of like your origin of a certain syntax system, maybe.
Yes, yes, and actually, this not to go too far along the tangent here, but this actually connects to the discussion that we were having around mathematical observers and how, you know, you might be, if you set up your whatever, this particular system, right, like the dot system, where you maybe I can be a little bit more atomic, right, like this, right? If I can erase, maybe. No. Why can't I erase? Is it crashing? I think it's crashing. Oops.
Well, I can erase. Turns out.
Okay, I think I'm back. Yeah, just it just glitched for a second. So, you know, this kind of system, just make it a bit prettier, where you have one dot goes to two dots, right? And all you're doing is looking at bags of dots, right? It's, you know, a bunch of dots together. This is pretty meaningless, right? It's just two dots on the page, like doesn't ring much. But it turns out that you can essentially do arithmetic with this, right? Because this is the successor function, right? Like you give me a term, I'll give you the successor. It will be, the new term will always be different, and therefore, you know, if your terms are all the possible bags that you can imagine, this is the integers and this is the successor function, and that's it. Like you can build all the mathematics, essentially all discrete mathematics, you can build out of this thing, right? So the point here is that alone, right? In my opinion, the information that's in that rule alone is extremely small, right? It is as small as it gets. So it is not really fair to the simplicity of the system for me to say, well, actually, that's the whole of arithmetic right there. I don't think that's good. I don't think that's a good sense of there being arithmetic there. What I think you can say is like, okay, set up arithmetic in some other way. For example, axiomatically. Okay, now you're defining, for example, the semi-ring of naturals or something, right? Okay, define it axiomatically, fine. That has a lot of symbols and that has a lot of like rewrite rules and whatnot as well, right? And then you will be able to, in this particular system, you will be able to find a correspondence between this sort of operation with the operation that might look like, you know, something like this in usual like semi-ring notation, right? Where you have an element of your semi-ring and then you do the plus binary operation with the additive, with the successor of zero. So it's like, you know, the multiplicative unit if you want, right? So, but that's just, you know, that's just an aspect of the semi-ring of naturals, right? That's not all the facts about the semi-ring of naturals. You have everything. You have, you know, prime numbers and, you know, Goldbach hypothesis. You have all these things within the semi-ring of natural numbers, but you don't see that in this rule. However, this rule induces a system that is to be found within the semi-ring of natural numbers as well, right? So in my opinion, a human user will say the semantics of that could be, you know, putting things together and aggregating, but what in a formal sense, all you're doing is actually somehow building a bridge between two very differently looking systems. One that has to do with variables and binary operations and things like that, which is the semi-ring of the naturals, and the other which just has to do with dots, bags of dots, right? And, you know, there's a possibility, you know, there's a one-to-one correspondence between set of elements, and there's blah, 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 some preservation of the rewriting properties of the systems and so on. And so this whole business that we discussed in the Institute about a year ago or so, that we were calling emulation of formal systems, right? The fact that you find an aspect of a system in another, and so that's why I think semantics gets tenuous when you try to very precisely give it a meaning. I think Nick nailed it when he said it kind of depends on the context, because some people use it in a very specialized way, and they, you know, semantics and syntax is to many computer scientists are, you know, these are very clearly defined things in their context of their operation. But when you really sort of push the limits a little bit, you realize, well, that it's difficult to pinpoint when something is the meaning and when something is not just syntax, and when it's a network of syntax relations, and so yeah. Anyway, but that's a little bit off the tangent. Let's go back to just rewriting itself, and just let's introduce a few terms. So we have some vocabulary that will come up a lot in the future, and in some sense, these are actually arithmetic is going to be my guiding example here, because I think it's clear enough and it's simple enough, and everyone went to primary school, I assume. So I think we are good to go with the prerequisites here. So yeah. So let me just list the terms here so I don't forget where I want to go. So we've had term, we've had rewrite rule, we've had a rewrite event, we have so what is the term here? I guess parent descendant. There is termination. There is confluence. And there is, I guess, cycles. So, okay. So these are some of the passwords that we throw around a lot when we talk about rewrite systems. And I think it's best to just illustrate what these things mean in context. So, of course, term, that's, I guess maybe I'll say /state. Oops. So term or state, that's the thing that you're manipulating. So in this particular case, expressions of arithmetical, combinations of symbols. Here, just bags of dots. It could be hypergraphs. It could be commutative diagrams in category theory. Anything that you're going to manipulate and that you have some way to represent and operate on, that's your term or state. So when you abstract your rewrite system as a directed graph to express the causal structure, those will go as sort of annotations or tags of the nodes of that graph, right? The element nodes would be those things, right? Now, the rewrite rule is a declaration of a pattern and a transformation of that pattern in context. So there are many ways of doing rewriting. There are many, there's a lot of flexibility in terms of what you consider a match of a pattern. There is a lot of flexibility of what you consider to be a contextual information that has to be preserved. And we are by no means trying to cover all cases here or trying to be exhaustive. We are quite focused on a kind of rewriting that works for hypergraph rewriting because of the applications that we have in mind. It turns out to be a very powerful one, so it's not that we are constraining ourselves a lot by restricting to that sort of rewriting, but it does have its specialty, and this is usually called a contextual rewriting, where effectively, and I'll explain here what contextual, and you will allow this K for context. So it's not just to appear cool, it's because the usual terminology in sort of the double push terms uses a K for context. But so contextual rewriting effectively has the following sense, which is very intuitive. So you begin with a term or state. And the rule intuitively gives you an output, right? So this is going to have some output, and it's going to give you some kind of information of where to match and what to assimilate and transform into the output, right? Okay, let's actually make it clear. So let's say that this matches a triangle and it outputs a circle, for example, right? Now, of course, if I start to draw shapes here, I might draw a square, I might draw a circle over here, I might draw two squares together, and then suddenly maybe I start to draw squares that have these kinds of things, and I have these kinds of things, and so on. Right? So if this is my rule, match a triangle and output a circle, well, it's not entirely clear what it means to just be a triangle, right? Because if you were just every time you see a triangle, just write a circle, just period, then in a way you're not really doing any rewriting. What you're saying is counting the number of triangles and then somehow saying that's the number of circles you get. But you're not saying anything about where the circle fits or how the triangle has to be either isolated or next to something else and so on. So actually, implicitly here, there's something that remains constant. So maybe you want to say something like this, that this had a circle that it was inscribed on the triangle, right? And now this circle is in context, right? Like this circle actually, this is the context. The actual triangle is providing the context. You could write something that is different from just the input, but for simplicity, let's consider the input. And so you're basically saying your circle will happen where the triangle was. It's like, right, okay. So then I can look at this diagram and say, well, I can do a rule application, for example, here, right? And so I will draw a circle over there. Or I can do a rewrite application over here, and I'll draw a circle over there, or over here, or over here, right? And so these rule applications, there are 4 of them. I'm just writing on top, just for simplicity, not to draw the whole thing again.
There's also the double one. There's this one.
Oh yeah, that's true. Yeah, there's another one there. Yes.
Maybe, so, depends.
Yes. Again, that's exactly where this becomes more subtle. Like you have to specify exactly what you mean, but yeah, that's the spirit. So the point is that maybe you want to say, no, this triangle needs to happen exactly adjacent to a square, right? And so here, like in your pattern match, you will have to say that this is a square adjacent to the triangle, but in your output, you will have to say something like, you keep the square on the side to the square on the side to the circle, right? In which case you go to this and then you actually find that there's this case, a triangle attached to a square. Like, okay, in that case I just rewrite it as a circle and I write the circle there, right? Or this one is attached, so that one I can write. So in that case, there are only 2 outputs possible, right? So anyway, this we identify as, there is, every time there's a rule match, it consists of 3 things. You have an input object, you have a context object, and you have an output object. And the idea is that the context object is going to appear in both the input and the output, right? So the context, you're going to have a term with a context k, and you're going to have a term. So context k where you find an input, and then you're going to have something is going to happen here. You're going to have a different term prime or something, with a context k, which will be the same, and then something else, which is the output, right? So this is where really the rule is applying, in some sense, actively speaking. So that is being modified or transformed, but it always happens in a context, right? So in terms of category theory, people think of that the context has inclusions in both so these are So like in theoretic terminologies, like this is included in the input, this is included in the output. So notably, there is no mapping between the input and the output. There's no sense in which the elements that make the input term and the output term are mapped into each other, unless you have some specific application in mind of these rewrite systems and you want to interpret them as such, like I do in my algebraic investigations. But in general, there's no mapping implied between these two notions. The general context is just the sort of space where you're going to operate. It's kind of your workspace, so to speak. The general term is whatever is provided for computation. The context is where you will find your input. So that's where you will find your match, your rule being matched. And then the context is basically your workspace. So you ignore all the rest, but you're going to do some operations within the context. But the context as a whole is going to be preserved, right? And you can think of it, the context, you can think of it almost like the boundary of your rewriting. It's like the kind of information that you specify at the boundary of things that are not going to change from one thing to the other. So in order to maybe give you another example that I mean some of our viewers might be very familiar with, and it's the one that I used earlier to illustrate in the case of categories. In the case of morphism composition or arrow concatenation or transitive closure, there are many names. When you have something like this and you express it just as a graph rewrite rule, it is clear that that graph there is an input. This graph here is an output, right? But then there's clearly the context in this case is just the three vertices, right? There's three things that remain constant. That's the context. That's the thing that you're scanning your entire thing for context first, right? You say, okay, I have a context here, I have a context here, I have a context here. And then in each of those contexts, you're going to scan for input patterns. And it's like, okay, I found this particular input pattern, then the context I keep unchanged, and then I apply my my rewriting there. Again, this is not the only way to do rewriting, but this is a particularly powerful way to do rewriting that we're focusing on. And I want to express it in this level of detail because people can see that there is a subtle art to doing rewriting. It's not just, oh, you just change things in some way, but actually you need to be very careful what your terms mean so that you can define this sort of game where you have a context and you have input patterns and then you change something and you get your output pattern and so you glue everything together again. That is a potentially non-trivial procedure, and Nick's been hard at work many times just trying to make sense of what that is exactly doing in Mathematica or whatever. And of course, if some of our listeners and viewers remember about hypergraph, the hypermatrix workshop, there were people whose last 10 years of research career has been dedicated at dealing with the intricacies and subtleties of these kind of questions, right? So anyway, just to give some general sense. So that's a rewrite rule, and that's a term and state. So as a definition, just as a sort of concluding remarks almost. I mean, I'll go over this other terms just to have some notion, but as concluding remark, as definition, a rewrite system is usually given by an initial term, a collection of rules, and that's it. And then what follows from that is the set of descendant terms connected via causal edges, right? So that little phrase there basically means, you can go back to your favorite example. So what was the initial term here, well, that expression 1 plus 2 plus 2 times 3. What was the collection of rules? Well, the rules of arithmetic, right? The things that you loaded in your, you worked really hard to burn in your brain when you were 5 or 6 or something. Right? Those were the rules. And remember that the notion of there being one or more rules is really not that important, in the sense that rule application is always context sensitive, right? So it's all about context of terms. So because we are leaving the initial term as arbitrary, anything can be an initial term to be considered as a rewrite system. A rule might apply in many different sites, right? In many different sub-expressions of an expression, or in many different subgraphs of a graph, or any other kind of sub-object or sub-term of a term. So there is, in some sense, no distinction between having one rule applying multiple times, or many rules applying once each, or many rules applying multiple times each, and having, there is no formal distinction between that. And certainly, if you had just the pure causal information, you won't be able to tell what's going on. You just will see that this state was transformed into that state, but you won't be absolutely positive that this was because this particular rule applied. Because you can imagine there might be states such different rules apply in different ways but produce the same output, right? So it might be that you can't spot that. But anyway, so that's the definition of a rewrite system. Basically, it's a very natural notion in terms of dynamical systems, because it's similar to how you set up a dynamical system. Hence the parallel in terms. So a dynamical system has an initial state and an equation of motion, or some kind of set of equations, right? So here, that's the analogy. The initial term are like the initial conditions, or the boundary conditions, and the collection of rules is similar to the equations that you set up, basically the things that are going to govern the dynamics. So some people, sometimes there's a little bit of ambiguity in either whether you mean the initial term and the collection of rules, period, or you actually mean the set of descendant terms connected via all the causal relations, meaning all the actual rule applications. So is this rewrite system the 1 plus 2 plus 2 times 3 and arithmetic, or is it this particular diagram? That is something that varies from author to author, or from community to community. But essentially, you can imagine that for finitary ones and terminating ones, those two things are one and the same, because obviously, when given one, you can generate the other. So it should be fairly clear. All right. So very quickly through these terms. So we now understand what a term is. Now understand what a rule is. A rewrite event basically corresponds to an edge in this terminology, right? To a directed edge of my graph here, of my system. And note that depending on the application, you might have the ability to track which rule applied. So in some sense, your edges might be labeled by the rule that applied them. Other times, you don't want that level of detail, and we just collapse and we just see whether there is an edge at all or not between these things. Or maybe you can count the number of edges that there exist, and so on. Now, parent and descendant, I think that's a fairly self-explanatory notation. So we say that a term is a parent to another term if they are directly above. And we sometimes, I guess I should also say ancestor here. So ancestor means that there exists a state is an ancestor to another if you can find the path in your directed graph from that one to another. And this is, remember, a directed path. This is a directed graph, so paths will have direction. So a parent is one where it's basically a generation one, generation Y parent ancestor, and then here you have child, and descendant. So descendant means that you can find a future derivation of, a later state in your rewrite system that gets you there. So basically, that you can find a path. So it's kind of the reverse relation. So again, these are directed graphs, and that's why they are not symmetrical. So being a parent, being an ancestor or being a descendant are basically the transpose to each other, but they're not the same notions because these are non-symmetric graphs. And then obviously being a child means that you are a generation 1 below. So that it also introduces the sense of generation. So a generation refers to the number of rule applications that have occurred, right? So here, for example, in this example, we have generation 0 over here, and then we had generation 1 over here, and then we had generation 3 over here, and then we have generation 4 over here, right? So these are just some countings of the number of rules that have occurred in this particular rewrite system for each of these states, right? So the first state is the first, so the 0. So the second two, there was just one rule application that happened, and so on.
So I've got a quick question on that for my understanding. So is there no way that this rewrite term could be said to ever happen in this generation? Like you would have to get here before you could get here.
Oh yeah. So the terminology, and this is a very good question because it clarifies something that might not be obvious to people who are unfamiliar with rewrite systems. So in a rewrite system, should have said this very explicitly before, but so thanks for the comment. So in a rewrite system, you take a term or a state, and then and your collection of rules, and you pattern match for all possible matchings, right? You just exhaust all possibilities, right? And then you do each of these independently, right? So each of these rule applications happen independently, meaning that in each of these occurrences, you take your initial state, you deform or transform or modify or manipulate, whatever you want to call it, the particular context and expression that your rule establishes, and you produce, therefore, a new state. There might be some cases where you actually produce the same state, but then same thing applies. But the idea is that you produce technically a new state, a new term, right? And so that term is already considered to be generation 1. So you always go back to generation 0, meaning your initial state, and you do all the possible rule applications. So every one of those, whatever the output is generation 1, right? So in this particular case, because there's only 2 atomic expressions that are already numerical and can be operated, the 1 + 2 and the 2 × 3, there's 2 generation 1 terms, each of one corresponding to applying it on the plus or at the times, right? So because we are tracking this rewrite system, you know that the term 3 + 6 actually needed to come through one of these 2 because we didn't have an atomic expression yet to get the 3 + 6. And so that's why in this particular case, that's why did I write? It was interesting. So that's why you need the intermediate step, because you can, the implied rule here is that it's sort of like the rules of arithmetic, right? Like just the multiplication table and addition tables and things like that you learn when you're a kid. So 3 + 6 has to be generation 2, right? There's no way to get 3 + 6 only with one rule application in that.
So could you say that this term and this term exist in the same generation? Is that like accurate wording?
Yes. Yeah. That's at least how I use the terminology, like generations from an initial state. It has to be said that this is slightly different to what, for example, Nick does with causal. Using as causal sets and causal structures, because the generations just refer to the number of rule applications, but they don't really have any notion of dependence, right?
Okay.
It's just really a way to count the number of times that a rule has been applied to a state, right? So it could be ambiguous because if you have a longer path and a shorter path, which one do you assign? It could be ambiguous. So, but you still can say that a particular state followed from a generation when you're following a particular path, and that's kind of
okay.
But yeah. So those to distinguish generations from from that more causally informed distinction. That I think that's what people call foliations, at least in the physics project. That's what you've been calling them, right, Nick?
Oh, somewhat. I don't think they necessarily should be generational.
Because there's anti-chains as well. Is that even something different?
Yeah, foliation. Yeah, it's just foliation is like all possible ways to slice your causal graph.
Yeah.
So that each slice doesn't contain any time-like events, right? But
Exactly.
you like in this example, you can put one of those events from first slice to the
third.
maybe to like intermediate slice between 1 and 2, right?
Right.
It's just this is just the most packed way to make a slice, right? You can like bundle a bunch of space-like separated events into a single slice, and you can call it the generation. But even generations sometimes can be ambiguous on their own. But
exactly.
Here, there's no ambiguous events here, but
there's no ambiguous events here. I agree, but like if we had a system that looked like this, right? Right. Like, which generation is this? Right. Like you could.
No, I think I meant by ambiguous. I meant something like different. No ambiguous in the form how you would slice it into generations, but events can kind of applied not like in a space-like manner, like independently in parallel, but they actually apply to the same thing, right? So that you can actually put it into a single causal graph in a way. You have to fork it.
Oh, you have to fork it. So
right,
is it kind of like if they don't reach confluence? You mean like that?
Well, they may still reach confluence, right? But you can't. But the events themselves, they apply to the same subterm, right? They're like different rules, or maybe there are different outputs of the same rule, whatever. There's like some ambiguity of applying an event to a term, so that you can't just apply them in parallel. You have to choose the order you apply them on, just either one or another, right? There's no way.
The order becomes important. The order of updating has become.
Yes, and I think what I'm trying to say here is that these are more refined things to do. So generation is really a sense of really a path, right? Like once you're following a rewrite path, then you obviously can keep track of generation, right? Because you know the number of times that you've applied some rule, right? But
so once you've identified a path, then you can sort of identify the generations.
Exactly. But anyway, so these are the concepts, right? The concept of being an ancestor, a descendant, in this sense of directed graphs, and then you have this implied notion of generation, even if it's sort of ill-defined globally for the entire system. All right. The other very important notion is termination. So because we are dealing with directed graphs and we're dealing with these systems that have sort of a element, process, new element, process, new element, there might well be, and because the process is based on a pattern matching mechanism, it might well be the case that some states just don't have any pattern matching, and therefore are also called, maybe another really concept here is inert. Inert with respect to a particular set of rules, right? We say that a term is inert with respect to a set of rules if there are no pattern matchings of those rules in that.
I think we call it just normal form. They just, it's like in the fixed point normal form. Nothing. It's no rule can be applied anymore.
Yeah, but actually, no. But I would hesitate to equate inert to normal form, because normal form implies some sense of standardization or some sense of algorithmic kind of procedure behind it. But inert, because you could have that you have several terminating states, right? But your algorithm always finds one, and you call that the normal form, right? So you could have like a system that looks like this, right? right? And so these two are terminating states from the initial one. So they are both inert with respect to the rewrite rules, but maybe your algorithm is so that you always choose the left side of this diagram, and so this actually ends up being the normal form, right? I mean,
Well, I don't
obviously,
know. Maybe
in Confluence,
I think there's like a
it's really the same.
maybe it's like a Chomsky normal form. I think there's a proper definition of it. Right? Maybe they're in this case. I think they're both normal in that context.
Sure, but I think I mean I'm not disagreeing. All I'm saying is that the term inert is just less committed to any sort of context, right? It's basically saying you give me, this technically this can be a rewrite system, right? Just give you a term and a bunch of rules, but they just don't apply, right? So then the only thing inert is just an adjective to say this is inert with respect to these rules, right? So definitely normal form is going to involve something being inert with respect to some rules. Confluent, terminating state is going to involve being inert. But inert is just an adjective, right? I mean, maybe you'd never use it as a definition, but it's just to say like it's just a short for there are no matches of this set of rules. It's like that's long. It's inert and it's short. I'm not trying to say that this is a defined term, but it's more like terminology to quickly refer to the fact that a set of rules don't apply to a certain state. Anyway, so termination is the phenomenon where this happens, right? So you are in a system and you find a state where this happens, the termination. So if you are thinking of this as a processing time, then your process ends, and that's why we call it termination. And when termination is more specific than that, but in the sense that you have the single terminating state, you call it confluent, right? Okay, let's revise it in a moment. That link, because I want to be sure that being standard here as well. And finally, cycles. I think I can be done with the whiteboard and come back to the presentation. So cycles are, in a sense, the opposite of terminating states, as you can imagine, but in a sense, the same as terminating states, because, a cycle, as the name suggests, is when you find a collection of states, that do something like this. Oops. Right, so that's a cycle. And the reason what I'm saying it's the opposite from a terminating state is the opposite because it never ends, so it's not terminating. But in another sense, it is the same as a terminating state because once you've identified a cycle within your rewrite system, you can be sure that you will never. I mean, it's not that you can be sure, but it can be that this is a terminating cycle. Right? It can be that all other paths in your rewrite system actually lead to these nodes, so these terms, and therefore your entire rewrite system is actually confluent to a finite set of terms that you would keep on rewriting forever. So you say, okay, that's fine. So take any of them, your favorite one or something, and just collapse it to a single point if you want or something. So, just like in the dynamical systems, you have the notion of an equilibrium point, but you also have the notion of an attractor, right? Where you have actually a subspace that is acting as some form of generalized equilibrium point or sink point or source point or something, right? So these notions generally apply to this. So let's double check the terminology. This is actually thanks for this, Nick, because I was gonna recommend the article on abstract rewriting in Wikipedia. Actually has a pretty good summary how to think about these things more mathematically. So let me actually just stop sharing this. Oops, not leave the meeting. And let me share the article. So this is what people call normal form in abstract rewriting. It says an object is normal form if it cannot be rewritten any further. So that's the historical terminology for normal form, and that's why I wanted to deviate a little, just to be able to say, as it says, depending on the rewriting system, an object may rewrite to several normal forms or none at all, right? So that's where the sort of what we could call a terminating object in this, or a terminal. I like to call terminal terms. Is what people call normal forms. The only reason why I'm not a particularly avid user of the term normal form is that it evokes exactly the rewrite systems that people have been working on, that usually have these algorithms to find normal forms and then use them as an element in their argumentation or the theory. Right? It's like, okay, put this in normal form and do this and that and that. Like that's important. But when you're just sort of globally looking at a rewrite system and just describing the features and just I think to me it makes sense to not be bound to the tradition of abstract rewrite systems and say normal form, which has a bit of baggage to that particular change of words.
They're actually differentiated there, but they talk about weakly and strongly normalizing.
Yeah.
So it can get quite technical. I think we're kind of like touching the surface of how advanced rewriting is.
Yes.
Even the Chomsky normal form here is talking about abstract free grammars, or no, context free grammars, and some other interesting mathematics.
Yeah, that's a special thing. I don't think it's. I just didn't know how this would be called, but Chomsky thing is just a different thing altogether, I think.
Yeah.
There are different ways of defining for different systems. There are different types of normal forms and all that. I think this is the most relevant.
Yes, definitely. No. So in that sense, I completely agree. I mean, normal form basically means that a term is inert in this terminology. But because we are presenting this sort of as a first introduction, I think it's always a good idea to have evocative terminology that is more direct. If your audience just knows about what is a term in general, what is a rule in general, to me it makes more sense. If I've never specified that terms can have form, because I never said that our systems are of a specific kind. They are definitely not made of symbols in like place notation or something like lambda calculus or all these more conventional systems. I think it makes more sense to just use words like inert or things like that just refer to the fact that something's doing nothing. And I speak from experience. When I learned normal form, I always assumed that there was, because I knew normal forms in some algebraic context, and I knew of those concepts in like very specified mathematical disciplines. And I was like, so is it just mean at all that there's only like no application of rules? That's a little bit weird. So it took me a while to like actually, because that tradition said this and that. So if you're thinking about rewriting, that's what you normally care about, whether rules apply or not, whether there are many applications of rules, whether you confluent, whether you arrive in the same destination no matter where you go, which is essentially confluence. But all these things can get very subtle. And if you explore this article, which is actually quite well written, it's mostly taken from, what is the reference? This one, the Term Rewriting and All That, this book. That's where most of this article comes from, and it's pretty good.
So would that be the bigger kind of umbrella system at play here, which is abstract rewriting system?
Yes. So abstract rewriting system is basically the left-hand side of the two branches that I showed in the separation. So abstract rewrite system basically means you focus on the causal structure of it and just how things are related by these directed edges, right? And you essentially, well, not essentially, but entirely forget about how the terms are being transformed. You only have the information that they can be transformed and from which can be transformed and so on.
Okay.
So in a sense, it's like it's a subfield of directed graph theory. I mean, in some sense, it's not like a potentially infinitary potentially labeled, potentially other things, but in a sense, abstract rewrite systems really, or you know, binary relations on sets in some sense, right? Like it's that kind of.
It's one of the areas that we're talking about. It's we're covering a larger surface area by talking about rewriting as a system itself.
Yes, exactly. So anyway, but that's, I think, I don't know, Nick, if you want to throw some other words or terms that we typically invoke and have not been mentioned.
And I don't know. So we haven't covered them all, right? Yet. You have some more terms in there.
Oh,
On the whiteboard.
Confluence was the last one.
Oh, yeah. I just closed it. Sorry to share this.
Well, from that list, I think maybe like causal relation, something like that is we also throw around pretty often because there are events, but we also have an actual causal links between them.
That's
I
right.
think those are also important.
So yeah, let me go back. Yeah, here we are. Yes. Okay, so Confluence is the property that it basically, no matter where you place yourself in the system, you will find a single, normal form in this more classical terminology, or in our more simple terminology, single terminal point, terminal state, inert state that leads you there. So I mean, Confluence, the word is suggestive of what it's really referring to, which is this idea that you can sort of go in a journey from some given point, but eventually you will come back to the same point, right? Like all roads lead to Rome kind of situation is when you say that your system is confluent. Again, this is a sort of overview perspective. There's like different degrees of confluence, and you want to specify sort of weaker or stronger notions in terms of what you are requiring pairwise for all your elements and things like that. But that's essentially the idea. The idea that if your system has a single terminating state and single normal form in this case, then you call it confluent. That's basically the quicker way to define it. And then, yes, I think.
What's the opposite of confluence then? Or do you want to first elaborate on causality before we talk about?
The opposite of confluence is non-confluence.
And so, I mean, the question there is, do you need a rewriting system that reduces in order to reach confluence? Like something that's infinitely expanding, could that be confluent in a certain way?
Well, remember that's why I really want to stress that there are these two branches to what a rewrite system is. So on the causal side, on the rewriting, the pure process side, there's no sense in which we are reductive or expansive, or because we have no access to the terms themselves, right? On the term syntax side, we definitely know whether we're being reductive or multiplicative, or and that's why I really wanted to separate them, because you can do a lot with each of these sides without any relation to each other. Right? We can do a lot of analysis. I mean, this is why I wrote causality, and maybe Nick should be the one actually talking about this more than me. That you have all the properties of these directed graphs that you interpret as processes, and you interpret as sort of timelines, and you interpret as like we do in general relativity, and want to infer these sort of systems of communications and signaling and all that. That can be the kind of framework of analysis of these directed graphs and sort of these abstract rewrite systems, and that uses no information whatsoever, or can be done without any information whatsoever about the actual terms. Now, if you go to the term side, there is a lot that you can say about certain systems just by looking at the terms, right? If I show you that rule that dot goes to two dots, you automatically know that it's a non-terminating system, right? When you define your states as all possible bags of dots, right? And so having access to the specific of the rule actually allows you to do some kind of rule self-composition, and you can derive a lot of properties of the system, and in fact just reduce the system entirely to something you already know. In this case, it's just a successor function and you're done, right? And indeed, you can say things like whether your terms have a size, for example. There are many instances in which a size is well defined for a term, and you can say whether a rule preserves, augments, or diminishes the size, right, of a given term. And this leads to interesting, when you have rules that are all reducing, then you know that and all your terms have finite size, then you know that you're going to have terminating states, because just basically the arithmetic of it. And I mean, that's assuming that you can't have like the cycles in your system with this some specific rule. So, but basically these things you can state about your Ruby systems based on just state syntax kind of, or term syntax arguments. But you can have all these analysis without it, right? You can so Confluence in a sense is really the statement that you will find a terminating state, right? That's essentially, and in a sense it's existence and uniqueness. So termination is that your system actually terminates, that it doesn't grow forever. So the opposite of termination is, non-termination, which means that you will find paths that will go on forever. But then termination can look like, this kind of trees where you have several endpoints, right? But if you have a Confluence, that's actually telling you that you have a unique endpoint that you get to, right? And so there's different people have different conventions, but you could imagine rewrite systems that are given by a single initial state or several initial states, and depending on that, like most often people consider one single initial state because they like to compare it to dynamical systems, right? But depending on application, we might drop that, and you might want to consider a bunch of states, apply rules to all of them, and then basically keep on iterating your rules on all possible states and generate the graph, the sort of state graph of that evolution, and just start to analyze from there. And that's where causality enters, and that's what Nick was mentioning, sort of causal relation. So maybe Nick, just give us a debrief. I think you'll do it much faster and highlighting what's really crucial for everyone. So either you share your screen or you draw on top or whatever.
All right, I can try to draw it something. Like I think that from that picture you have there, it's like whatever was missing is just a simple idea of just having an event, right?
Yes.
Oops. Hold on.
Oh, yeah, you were following. Sorry.
Lost my. Where am I? Okay, there you go. Okay. Dun, 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 dun. Okay, so there's like an event at each all of those events. You can designate some kind of event there, right?
Yes. Yes.
Okay, if there are two events there, only I could do it like this. No. Right?
Mm-hmm.
But there's also, maybe the example might be too simple, but it's fine.
Yeah. That's maybe I'll erase the generations just for clarity.
That's a big arrow. Round arrow. Let's make a different.
Just draw it. Maybe.
Yeah, I was going to like this. With me. Like nicely. I wonder if there's like a shortcut so that they don't have to choose an arrow every time.
Yeah, we should maybe experiment with
Try
some of the
different-
other whiteboard systems. Find a confident one that we all agree on.
Yeah.
I think not of the obvious shortcuts. But anyway, it's like, yeah, so there are events, which is the edges in this term rewriting system, right? And whatever we call a causal link or a causal connection between those events is just the obvious thing of the dependency between those. Just this is the way to represent dependency between those events. Some events can be non-dependent, like these two events right on the top, they're independent, so we say they're space-like separated because they act independently and can be executed in parallel if you actually want to reduce this term by the rules we are defined, right? But some of them are time-like dependent, like these two events on the left side. They are time-like separated, so they only can be reduced in sequence, one after another. So there's like if we had a system that also had this ambiguity where the rule applies to the same subterm, but in two different ways, then it's like another way of separating them. And what we usually call branch-like separation, right? Because we're creating a branch or fork or whatever, so that in order to represent this ambiguity, so that we just show all possible combinations, we can apply this rule to the subterm.
So would this be branch-like, and then this would be time-like, something like that, in this example?
The other way around.
Other way around. Okay.
The vertical one would be time-like.
Okay. Yeah, I'll split them up the nodes on this side and the nodes on that side. Yeah.
Okay, yeah, I kind of get it. Yeah, okay. Left and right are time-like, and all the horizontal ones are space-like separated. Well, I don't know what else to say about it.
So
it's kind of very.
I have one question that's related to this that somebody asked recently, and that's is causal invariance the same as confluence?
I think there's some debate about it. I'm still not sure. Yes, I think the definition, at least for the causal invariance, was that okay, you run your term rewriting system, right, and you get to the same term, right? But that's what we call confluence. But it may be not causal invariant, because causal invariance is when those different paths that you reach that normal form or whatever, but produce different causal graphs, like on the term of whether those causal graphs is isomorphic or not. So they can be different causal graphs. So even though it's a confluence system, but the way you reached your final outcome are different in the terms that you kind of lay out the different space-time.
So you could have a confluence state that was causally invariant.
Yes, I think so.
I mean, causal invariance is kind of a term that we coined. Is that correct to say? Like that doesn't exist in the mathematics literature, Carlos? Or does it?
Well, I'm not sure.
I think it is. There's still some confusion about it. It's like, I think I remember like Jonathan Gorard arguing with Max Piskunov about what does it mean. It's like there's a bunch of counterexamples. It's like, it seems like if it's, I don't remember what's the argument was, but I think it's like you can have an example in both ways. You can have a confluence system which is not causal invariant, and other way around. You can have which kind of makes obvious, but for some reason it wasn't so obvious because otherwise there wasn't been any argument.
What was the definition again of causal invariance precisely?
Just having isomorphic causal graphs of the different paths you reach the same state, right? In the multi-way system, if you have a multi-way system, which is your all-encompassing term rewriting system, you just write down all the possible events, right? And you pick a state, right? Maybe it's a single state. If you, for example, you're reducing the combinator expression or something, right? Combinator expression can be reduced in different ways. So it's confluent, but if you just pick a path and just draw the causal graph for that path, it's not isomorphic to the causal graph of another path.
Would it be like this example here? on the left. Like this is
Yeah.
one causal root and this another causal root.
Yeah, it's like this is not obviously not causal invariant because it even contains different number of events.
Yeah.
So
Wait, but I feel like, I mean, if you're just looking at paths, right? Their causal graphs are always their causal graphs are always going to be path graphs, right?
no, not necessarily. You in the in a multi-way system, obviously it's a path, but you can unroll. You have a path of events, but those events have different causal links between them. Their dependency are different. And as soon as though you record this information about how those events are related to each other in the path of the multi-way systems, you get a causal graph, and you can have different causal graphs for different paths of the multi-way system. So in a way, causal invariance is much stronger property.
Oh, wait. So you're using, I see. So you're using all you're using the entire multi-way graph to draw the causal relations of the single path that you've chosen, right?
No, I'm not using it. It's like pick any multi-way system, right?
Sure.
You have like here on the left. It's just have two paths,
Sure.
right? Each edge is an event. If you actually draw the dependency between those events, in this example, they're obviously going to be different because they will have different number of events, like 3 versus 2 on the left and right. But you can have much more complicated dependencies between them.
But that's what I'm saying. But in this example, both causal graphs are path graphs as well.
Right? No, they're not. Those events. This is the multi-way system, right? Those edges can be actually, well, if you maybe again thinking in terms of generations. I'm just thinking of just local rewrites, maybe, right? Just like not just all possible parallel applications of those, and you just bunch them up into a single event, right? Those edges in the multi-way system connected side by side, they can still be space-like separated. They can still be events that can be applied in parallel, even though in multi-way system we just draw them differently, right? It's just there in the multi-way system you have to make a different part that has this application of events in a different order, right? That's it. So if you just if they're just for space-like separated events, you have two different paths that apply those events in a different order. You will still have the same causal graph, right? So this is like causal. They would be causal invariant in a way if you're just switching all the order of space-like separated events in the way you apply them, right? But then when there is actually a different path that reaches your target in a completely different way, even like using a different number of events, then it basically says that this system is not causal invariant.
I don't disagree with anything you said, but I'm confused when you tell me that the causal graphs of the paths in this particular case are not path graphs. I mean, no. I can draw them. I can clearly see they are path graphs, right? Like, how are these not two?
No, it's like imagine like this event.
But Nick, in that, yes, there, yeah.
In this event, right?
Yes.
They may be space-like separated. There's no causal link between them. You can apply them in parallel. It's just for this particular path, you apply them in this particular order. But they're actually, if it's a complete multi-way system, there should be like another graph that applies them in a different order. That's it. If you actually like it's the actual multi-way system. So this isn't just the same. This is like these two events are the same events, but in a different order. But they have the same causal graph, which with these two events at the beginning being space-like separated. You just can apply them in parallel. That's it. You just multi-way system just represents all possible ways you can apply them.
I'm confused.
Is this example up here more helpful in terms of it's kind of the same structure, but you can either do green and then purple, or purple then green, and it gets you to the same end location? Like, is this causally invariant, or is this the same causal structure?
Well, it depends what are those events. If you draw in the multi-way system, right? It's the multi-way system of the causal graph.
Yeah.
Okay, so one basic
What is
question.
it? Which
I
one?
need to ask
It's the
one basic
multi-way.
question because otherwise I'm getting too confused. So when we say the multi-way system, are we assuming anything other than a multi-directed graph?
No, just a multi-directed graph. But we actually, yes, but we rewrite in terms.
Okay, but this is where things are getting a little bit more complicated because so you say, I mean, the way you present you describe the causal graph, right? The causal relations between the edges here. Like in this example, these are path graphs. By path graph, I mean, like edge goes to edge, right? Like these are length 2 paths on the causal graph, not on the states graph, but on the causal graph, right?
Yeah.
Sure. So what I'm saying is, if the way you phrased causal independence was by saying you pick a path and you compute its causal graph. That's what you said.
Yes.
So I cannot see how a path ever has a causal graph that is not a path again.
Because well, that's what there's an example I draw it, right? Like this is the causal graph, right? And this is the multi-way system on the right. If you don't, well, let's just make a concrete example. What are those two events can be? Well, it can be this graph that you already have. It's just right you just one event is actually rewriting your 1 plus 2, another event rewriting 2 plus 2 times 3, right? You can do it, but you can do it in a different order. So in the multi-way system, there would be 2 different paths, but the causal graphs would be the same, with two events being space-like separated.
The causal graph is the same. Okay.
The causal graph is the same in this example.
Yes.
They are isomorphic.
Yeah. So anyway, this is like causal invariant property.
Sure, but nonetheless, they are path graphs, right? I don't see how this shows what I'm trying to ask, because they are path graphs.
What do you mean the path graph? They're path graphs.
Maybe that's the problem. A path graph is a chain of arrows, right? It's a graph that looks like this, right?
Well, actually, the way I drew the arrows may be incorrect and confusing. Like this arrow actually isn't correct, I think, because what is it?
So it's the events become the nodes of the.
Yeah. Of course.
See, they actually like this, right? These events are completely independent. It's like I wasn't correct to draw a causal arrow there. There's no causal link between those events. They don't depend on each other, so it's not a path graph. It's like this event and this event can be applied in parallel, right? If this is just applies to the left term 1 plus 2, this one is actually applies to 2 times 3, so they can be. So they're independent. So
wait.
It doesn't make sense.
Wait, but then it's more than a directed graph. It's a labeled directed graph.
Wait a minute. It's
well,
labeled. Well, it has some meta information about events.
Well, that's a lot more than directed graph. Yes, that's what I mean.
Well, but you can drop it. It's like you derived it using some information from the actual writing, but you just record the actual dependency between events. And that's maybe all you care about.
But that's, I think this was very important to highlight at the end of this session, because this is where the 2 branches, I insisted so heavily on these 2 branches, because most of rewriting theory happens on the left-hand side, and it literally only assumes directed graphs, right? In a general sense, in a potentially infinitary sense, right? And term syntax and semantics has this notion of what actual event happened. Like, was there actual overlap between the 2 events, or were the events somehow entangled, right? Were there some dependency, which is what Nick is talking about, right? And so that's why I was so confused, because if you can define you can define causal dependence just from the directed graph, right? Because that's already like some causal structure, and you can basically, transitive closure of that. It gives you some causal relation, but it's the obvious thing, right? But obviously, when your rewrite events have some internal structure, which was the thing that I wanted to sort of say in the end as a conclusion, because that's kind of what we are working on more actively, is like you have to define what it means to be dependent or independent, and that's going to be very sensitive to what is a context or what is an input.
Oh yeah,
right.
Yeah, that depends on that context K.
Exactly.
Like in this case of expressions, which are like tree-like data structure, the context is essentially like a position in the tree, right?
Yes.
If you're writing the same node with different rule, right, again and again, and like one after another, they should be dependent on each other because you're applying it at the same node. But if you apply it to like different branches on the tree, you can apply them independently.
Exactly. Yeah. Exactly. So that's what I was saying, that this level of analysis actually mixes both sides of the question. Right? It mixes and correctly mixes that. Right? Like it's the full story, so to speak. But in a sense, you can talk about causality just in the sense that you have a dynamical system. So you can define future cones and past cones and things like that just with the information of the abstract rewrite system that completely forgets about the details of the actual rewriting. I'm not saying this is particularly interesting for us, but if we are saying we're giving a general introduction to rewriting, I think it's important to point out. And then truly what Nick is saying, and that's what I wanted to end up with, is that we actually need to be very careful about what it means to do a rewrite in terms of the context and the pattern matching and so on, so that we can establish these kinds of connections. Because so that was my disconnect, that I was actually just operating in this assumption that we only have a directed graph, but actually we have more. We can go into the terms and
but two directed. I just don't get it. It is a directed graph, the causal graph.
But it's not
right?
just a directed graph. That's my point.
What do you mean by it? The way you derived it, maybe.
There's more information than a directed graph. That's what I'm saying. In the system, you can look into the terms, right? Directed graph doesn't have any information. The nodes are just primitive.
Well, you can say it about every graph. It's like came from somewhere. It's not like just appeared from nowhere. So some information, some semantics is there about how this graph was being constructed.
But I guess my point is that I'm using a mathematical way of speaking, right? Mm. If I'm saying mathematically, what I have is a directed graph, period. Mm. I mean that and only that, right? I'm declaring that I have the structure of a directed graph. That's all I'm declaring.
That's the only axioms that you're working with under that system.
Yeah. It's a basic information that, so if I say I have a directed graph that further has some state mapping into a term vocabulary or a term set, then sure, yeah. I mean, there's more.
Yeah. I think it's like the difference between causal sets and algorithmic causal sets. It's like in the theory of causal sets, they just deal with causal graphs essentially with no information, with no labels. So you just sprinkle them on some Minkowski space or whatever and study this, right? But when you deal with algorithmic sets, algorithmic causal sets, you actually have a procedure to construct them. And this procedure also, of course, leaves the trace of how this construction was done about all the individual term ratings for each event.
Yes. But I think this was a case more of, and I think this happens often when we are communicating, that, the mathematical way of speaking usually is when you say you have X, you normally say you have X and only X, right? Like in terms of information availability. So when I say my rewrite system is a directed graph, it means that it's a directed graph. And if I don't say more, then I don't know what I can provide, because you could also say, oh, and by the way, you can assign some metrics to each of the nodes. And by the way, you have some colors and the edges have some types, and this will all add more structure and you will be able to do more refined things. But if all you have is a rewrite system, the rewrite system in abstract in this left-hand side of just purely the causal structure, that is purely a directed graph. And that's, that article in Wikipedia is precisely that. It's just that it begins like the abstract Rewrite system is basically just a relation on a set. You have a set of terms and you have a relation among these terms, and that's it. That's an abstract Rewrite system.
By the way, while I was browsing Wikipedia, I also been reminded that there's like abstract rewriting system, right, and term rewriting system.
Yes.
Okay, because we mentioned a bunch of terms, so there are definitely some kind of difference. Definitely. And I think what we missed is the actual notion of variables. Because that's the part of term rewriting system, very substantial part. we haven't mentioned at all.
Yes, exactly. So that's why. So a term rewriting system will have a side. I mean, that has to do exactly with the syntax and how you express what can be rewritten and what is rewritten and so on. The whole point of not needing the specifics is that you can just look at your system and establish this causal relations. And of course, what we are doing in our research, especially in what turns out to be this I think I mentioned this at some point in either my introduction to my research or one of the first sessions that we did. Maybe it was one of the Explore and Learn. I said that there's this seeming powerful unifying thread that anywhere from fundamental physics in the observer effects in relativity and quantum mechanics to axioms in mathematics to the well-definedness of algorithms, like all algorithmic complexity, all these kinds of questions that they're very broad and seemingly unrelated, they all seem to have at the core this fact of, if you actually know what the entanglement is for your terms and what the dependence of your term rewriting is, you actually have a powerful way to identify phenomena that you're interested in. And in my case, that's all these mathematical theories that mathematicians have selected from the computational noise of the Rulliad, if you want to think of it that way. And in the case of fundamental theories of physics, it seems to be like the foundation of causality and the foundation of what observers are and all that stuff. So that requires a very tight control on what the terms are and like what it means to be dependent or independent. So, for example, in our current implementation in the multi-computation backlit, two rule applications are considered to be dependent if they share any elements at all between their pattern matchings, right? So, so if they share nodes, that's fine. If they share edges or whatever, that's fine. Like, but in some situations, sharing nodes is clearly so if your rewrite rules only apply to edges, only sharing nodes is not enough to actual causal dependence, because the nodes might be just on the periphery, and if the edges are just incident to each other, there's not going to be any causal dependence there. So this
you have to like actually compute how some form of commutation relationship between those rules, right? They may be applied like in the same space and the same subterm can be written, but they can be written in any order. Then it's as well as saying that they are actually causally independent, right?
Yeah.
And you can apply them in a way in parallel.
Yes, exactly. Yeah. So that's exactly the notion of being causally independent. I completely agree with the notion. I think with the concept we are fully in agreement, but it's more about how we are formalizing it and implementing it that it gets into these subtle territories. And we got into this debate about the branchal graphs and how to define the branchal graphs and the dependence there and so on. And this all has to do with this sort of subtlety of exactly the syntax and how the context is going to be seen by the pattern matching and so on. So that's basically why I'm just trying to explain why we got to this point where like, oh, this is still kind of shaky, because this is really where we are kind of developing in a sense, and audience should not be discouraged that rewrite systems can be quite approachable and simple, but obviously when you have specific aims in mind, you have to really sort of tinker with the detail, and that's what happens there when you actually have insight into the states and you can define relations between events because you have more information than just the fact that there's a directed graph. right? Because so Nick, that was my problem, right? Like I was looking at that graph, and I was saying the naive causal relation between sets is basically just the transitive closure relation, right? If you can find a single edge in the transitive closure, then your edges are related, right? So anytime the transitive closure rule applies to your directed graph, then you have a causal relation, which will be the graph that you draw earlier, like with the 2 arrows here.
Yeah, that would be like pretty trivial. I was calling it at some point like just pre-causal graph. It's just the causal graph without any notion of dependency. It's just purely graph theoretic. You just take whatever your multi-way system is and just it's essentially like a line graph, and maybe transitive closure of the line graph, right? You just compute purely from graph theoretic principles. But then when you apply the actual notion of dependency, then you get the causal graph.
There you go. Okay, that was important to clarify, and I think this was clear in my mind, but I think it was good to have it live on the stream that's how causal graphs proper appear. You need to have some insight into the rewriting process, and so you will get more information out of the causal graph because the causal graphs will contain or encapsulate more information than just the state graphs with bare nodes, right?
Yeah. No, I think you can recover both of it from each other. Maybe it's like the right. You can recover the states graph for all the information of the events, and you can obviously recover from the multi-way system all the causal graph.
Well, I mean, if you have the information of the events, which is the full information, yes, of course.
Yeah, sure.
Each event is an input matching with context and so on. So yes, so absolutely. But yeah, anyway, I think that was I think in the beginning we had an overview, and then it was very good to clarify this thing because I was confused myself at one point, and now I'm perfectly clear-minded. So happy to carry on going with this.
So there are rules with which to philosophically discuss rule rewriting. Like you need to establish what you're talking about. You need to say like, we're talking about mathematics, we're talking about physics, and like what are the rules with which we even try to talk about these things?
Yeah, it's mostly not assuming more than like my philosophy is never assume more than what you say. It's like, but in this case, it was just my lack of information. That's right.
Just a quick one to maybe more in the context of if there's more to discuss on a part 2 of this. And this idea came up recently, and I heard this discussed a lot, but the idea of a DAG, DAG, is that like, and does that fall under rewriting? Is that part of this sort of idea? Does that be?
So a DAG is just an acyclic directed graph, right?
Acyclic directed graph, okay.
Yes. So never be dazzled by acronyms.
Okay.
It's like, because I mean, when you actually break it down, you say acyclic, okay, no cycles, directed graph, okay, done it. Like you don't have to ever think too hard about DAGs anymore. So I mean, DAGs are important because they certain what was the result? I don't know if I have it off the top of my head. So some very broad class of terminating rewrite systems are finite DAGs, essentially, because if actually
finite directed acyclic graphs. So
finite directed acyclic graphs are finite DAGs, or what people usually call DAGs because finite is assumed. Actually, that's just right. Yeah, DAGs are just terminating redirect systems, right? I'm not going crazy here. In the abstract sense, in the abstract rewriting system sense.
Are you asking us if you're not going crazy, or are you telling us you're not?
No, I'm mostly asking Nick, but that's right.
No, you wrote that the rewriting system is like initial term and collection of rules, right? Or maybe you actually apply them for all those rules.
In the sense of the generated graph, right, of a rewrite system, right? If your system is terminating,
Yeah.
and you allow for, with the flexibility of allowing for possibly many initial states, because otherwise you are going to have some topological constraints. I think terminating rewrite systems are all possible DAGs. Meaning all terminating.
Can you actually recover if you just given a random DAG? Can you construct a terminating rewriting system having this DAG? I think it's not a trivial property. It's not a trivial task.
It's not a trivial task, but it feels very possible. In a sense,
well, I still wouldn't define it like that.
I'm not defining it. I'm not defining it at all. I mean, I think this might be a result, but
especially that there's for maybe this different rewriting systems can give the same DAG.
Definitely, yeah.
I wouldn't call them equivalent.
No, I didn't want to say they were equivalent, because they gave you, or I say they are, but they are as in their graphs are, terminating rewrite systems graphs are DAGs. That's the phrase that I really wanted to say. I never implied they were equivalent or something, but it's
maybe are DAGs. It's weird. Maybe just they produce DAGs, something like that.
Yeah. The language was weird. Yeah, I agree. They produce DAGs. Yeah. That's the phrase. Yeah, sorry, but yeah, DAGs. DAGs are interesting because they, in a sense, in the spinal graph business, actually, when thinking about how you want to encode some kind of relational structure of some finite set of nodes, and DAGs are essentially the complement of anything that has an symmetry, right? So for us, having some kind of explicit symmetry meant that you could find some permutations of your elements, which essentially amount to having some cycles among your nodes. And so being acyclic precisely means you don't have those. So DAGs are the most general non-permutation symmetric spinal graphs. If you had any intuition for spinal graphs as things that kind of classify the sort of data structures that you can have, because you can have just two floating nodes, or a pair of nodes connected by one directed edge, or a pair of nodes connected by two directed edges, and that's kind of the distinction. So DAGs are just acyclic. There's nothing particularly profound because they are called DAGs, and some people will call us digraphs or digraphs. That just means directed graph. I mean, these are easy to be. I mean, I myself, because I am not a discrete mathematician, I wasn't trained in this stuff. I myself sometimes get dazzled. It's these names.
So is a dagger something else? You've heard you use the word dagger before. Or
digraph.
Digraph.
It's a digraph.
Okay.
Digraph is just short for directed graph.
Okay, so I've heard you say DAGs. I thought maybe those are daggers. Okay, no, that's something else.
No.
Okay.
No, DAGs are.
Well, there are daggers. There are dagger symmetric monoidal categories, right?
Yeah, daggers. Yes.
Yeah.
You have daggers.
They're also important. You have daggers.
Yeah, daggers are important. Nothing to do. I mean, everything to do with directed graphs, actually, as we know from my rewriting argument, but because a dagger is just a rewrite rule that reverses the direction of a directed edge.
Got it. Okay.
But anyways, these are all funny terminological loops. So very much not a acyclic graph of terms.
Just to disambiguate those terms there. Okay. Now I actually learned a few more terms.
This was useful.
I'm developing a syntax for my rewriting semantics.
Nice.
Okay. That was really fun. And definitely explored and learned a lot during that session. So thanks so much, Carlos and Nick, for going deep on that one. And there's some interesting things happening on the Discord. Definitely want people to join in there. We just concluded the attendance of Wolfram Summer School. So there's some content that's going to be coming out on the channel from that. So we've been quiet on YouTube for the last couple of weeks, but that's because we were doing a lot of in-person things. So yeah, stay tuned. In fact, tomorrow we are going to be doing our first project presentation from one of the students or alumni now that have come out of the summer school. So interesting new ideas and different kinds of fields of science that's going to have content that we can share with everyone. So yeah, stay tuned for that.
Looking forward to that.
Cool. All the best, guys. Chat soon.